Okay, section 1-5, 1.5 is about inverses. And there are a couple different ways to move or to find inverses. So let's define it. So inverse functions and relations is what it really is. So the definition of an inverse is two relations, f and g, are inverses if and only if both of their compositions are the identity function. And the identity function is y equals x. So if you do the composition, which is what we talked about last time, that means that f of g of x is equal to x, and that g of f of x is equal to x. If you do the compositions for both of those functions, then that means that they are inverses of each other. So they don't have to be equal to each other, they have to both equal x. And the notation, just so you kind of know this, the notation is usually for inverses. So if you have a function of f of x, f negative 1 of x is the inverse of f of x. And this may seem familiar to some of you. And that little negative 1 is not necessarily the exponent, it's just part of the name. It's not the exponent. So our first example we are going to do is to use the definition of inverses. So the def of inverses to show that f of x, which is 6 minus 2x, and g of x, which is 6 minus x over 2, are inverses of each other. So that means we have to find f of g of x and see if it's equal to x, and then we need to find g of f of x and see if that is equal to x. And if they are, then they would be inverses of each other. So first of all, f of g of x means we are plugging in what g of x is for x in our f equation, so 6 minus x over 2. So that's going to go in place of x in my f equation. So I'd have 6 minus 2, and then x is going to be 6 minus x over 2. So make sure you use your order of operations and do everything in order and algebraically correct so that you can get it. So multiplication, or whatever's in parentheses, should come first, but nothing we can change inside there. So multiplication is really like this 2 over 1 being multiplied inside here, which 2 over 1 times something that's 6 minus x over 2 means that our 2's essentially are canceling. So that would mean I would have 6 minus x, which means I need to distribute the negative into both of these parts, so that would really be 6 minus 6 plus x. And 6 minus 6 is 0, 0 plus x is x, so sweet, we're halfway there. F of g of x equaled x. So then, for this one, we're going to plug whatever f is in place of g, or in place of x in our g equation. So g of an f of x is equal to 6 minus 2x. So I'm plugging in 6 minus 2x in place of x in my g equation. So that would be equal to 6 minus x, and in this case our x is 6 minus 2x, divided by 2. So I'm going to distribute my negative in. That's going to give me 6 minus 6 plus 2x all over 2. If if I simplify the numerator, 6 minus 6 is going to be 0, leaving me with 2x over 2. So that simplifies to just be equal to x, which means that one worked as well. So yes, they are inverses. That's how you would verify it. You can also verify, inverses have a graphic relation. So inverse relations. We're calling them relations because they're not all necessarily functions. So inverse relations are reflections of each other over the line y equals x. So they're mirror images over that line. So if f and g are inverses, then every point would be reflected as its mirror image onto g of x. So what that means is, so basically, if f and f negative 1 are inverses, then the x's and y's are switched. So f of a equals b would be only if and only if, that's the abbreviation for that, their inverses, those letters are switched. So those values are switched. So if we're going to go back to the example that we just had, that was f and g again, I'm going to show the graphing. So I'm going to say, for this little example, to graph f of x, which was 6 minus 2x, and g of x, which is 6 minus x over 2, to see if they're inverses. So when I graph those, I'll graph them in the calculator. Let's see, I can't see all of that right now. Oops. There we go. So if I'm going to graph those, we'll go y equals, the first one was 6 minus 2x, and the other one was, in the numerator we have 6 minus x, and in the denominator 2. So if I hit graph and I look at them, they should be mirror images over the line y equals x. So there's the first one, here's the second one. If it's kind of hard for you to see, you could also graph the line y equals x and compare that. So imagine if we folded this on that black line, would it be mirror images of each other? Which, yeah, in this case it would be. So you can kind of see this would be a mirror image with this, and this would mirror onto that. So those are inverses. If we could verify that graphically on your homework, when asked to verify inverses, you can feel free to do them graphically or algebraically. Okay, so finding inverses algebraically, that's what we're going to do next. So there are a couple steps. So we'll say finding inverses algebraically. So steps would be to do this. Replace f of x with y. Then we want to switch our x and y's. And then solve for y, solve for our new y. And then replace y with the name of the relation, so with f negative 1 instead of y, so that you can clearly see which one is your inverse and which one's not. So we're going to find the inverse, so this is an example. Find the inverse of f of x equals x squared plus 1. And then we'll do a couple other examples. So this one, this is a function, parabola. So our first step is to replace f of x with y. So I'm going to rewrite it as y equals x squared plus 1. Then I want to switch x and y. So this is going to say x is equal to y squared plus 1. And you only switch the actual x and y variable, not the coefficients or the exponents. And then we're going to solve for a new y. So I'd subtract 1, x minus 1 is equal to y squared, and then take the square root of both sides. When you take the square root of both sides, you have to put a plus or minus in front of that. So plus or minus in front of what you're taking the square root of. So you end up with y is equal to plus or minus the square root of x minus 1, which technically means two separate functions, which is okay. And then the last step is to replace y with f negative 1 of x. So f negative 1 of x is equal to plus or minus the square root of x minus 1. If I wanted to verify that graphically, I could do so. I could graph f of x, which was x squared plus 1. I could graph the inverse that I got, which technically has two parts. So the first one is positive square root of x minus 1, and the other one was negative square root of x minus 1. And then I'm going to go ahead and graph the line y equals x again, just so you can see that it's reflected over it. So here's my first function, and then the inverse is going to come in two pieces. There's the first piece, and then there's the second piece. And here's the line y equals x. Does it look like it's reflected over it? I think so. Yes, it is. So that kind of verifies it for us. So this is the inverse of our function. Just because our relation is a function, our original one, doesn't have to mean that the inverse is a function. Okay, let's do one more example like that. So we'll say for this example, we're going to find the inverse of g of x is equal to x plus 1 over 2x plus 3. So find the inverse. The steps are to first replace f of x with y, or g of x with y, whatever we're dealing with. So I'm going to say y equals x plus 1 over 2x plus 3. Then switch all of our x's and y's. So that's going to make it x is equal to y plus 1 over 2y plus 3. And now I need to solve for y. So this is maybe a little tricky. That's why we're doing this. Because once you see it, you can use these algebra skills to do your assignments. So I'm going to get this out of the denominator by multiplying both sides by 2y plus 3 over 1, and multiply this side by 2y plus 3 over 1. So my 2y plus 3's will cancel right there. That way I got it out of my denominator. And I would have to distribute my x here. So I would have 2xy plus 3x equals y plus 1. And now I want to get every term that has a y in it on the same side and every term that doesn't on the other side. So I'm going to subtract y from both sides, and then I'm going to subtract 3x from both sides. So that's going to cancel right there, that's going to cancel right there. So I'm going to have 2xy minus y equals, you can have it written out either way, so 1 minus 3x. So I can't combine these because they are not like terms, but I can go ahead, and this is the step that you may not recognize. You can factor a y out of each of those. So if I pull a y out, I'd be left with 2x minus 1 equals 1 minus 3x. And then to get y by itself, all I have to do is divide by 2x minus 1. So then I would have y equals 1 minus 3x over 2x minus 1. And then I'd replace my y with f negative 1, or I guess in this case it's a g. G negative 1 of x is equal to 1 minus 3x over 2x minus 1. You can verify that on a calculator if you'd like to. I'm not going to do it for this one. Cool. So the other part is knowing whether the inverse of a function is a function. And if, so to tell if the inverse is a function, that means that it's one-to-one. So a one-to-one function is a function whose inverse is also a function. So if you want to just test to see if a function is one-to-one, you can use, so it has to pass, so the vertical line test, which is just to tell whether it's a function, but it also has to pass a horizontal line test if you want it to be one-to-one. And if it doesn't pass a horizontal line test, that means that its inverse is actually not a function, so it's not one-to-one. So if we look back at this, our original, one of our graphs, this x squared plus 1, if we just look at that graph, it passes the vertical line test okay, but it doesn't pass the horizontal line test, which would mean that it is not a one-to-one function. It's a function, but not a one-to-one function. Cool? Okay, the last thing that we're going to do is this example. So we have this function, f of x is equal to the square root of 2x minus 3. And we want to find the inverse and the domain, including any instructions or restrictions. So find the inverse and domain of the inverse, including any restrictions, including, and we're going to say this, including any inherited restrictions. So it's going to inherit the restrictions from its original graph. So remember, for a domain of this, that means that we can't take the square root of a negative, so 2x minus 3 has to be greater than or equal to 0, which would mean 2x has to be greater than or equal to 3, or x has to be greater than or equal to 3/2. So this domain that is starting out with for our function would carry on through to our inverse, whether the inverse has that restriction or not. So if I find the inverse, I'm going to go ahead and kind of switch the x and y at the same time. So x would be equal to the square root of 2y minus 3. And that's already switched in x's and y's, and I got to solve for y. So to get rid of the square root, you would square both sides, and that would give you x squared is equal to the, not square root, we just got rid of it, 2y minus 3. Then add 3 to both sides. So x squared plus 3 is equal to 2y, and then divide by 2. So our inverse function is x squared plus 3 over 2. However, the domain of that function would be all real numbers, but the domain restriction that came from the first one is inherited, so it comes with it. So you have to specify that this is for the domain 3/2 to infinity only, not for negative infinity and positive infinity. So there would be that.